So this is lecture 34. We're still putting together the finite element equations that we need to solve, which are shown here. So last time we completely defined how we would construct the C matrix and the K matrix. So we have sort of the left-hand side of this set of equations done. So now we have to move on to the right-hand side of the equations, and that includes this generation vector G, which is related to an area integral over the entire computational domain. And then we have this Q vector, which is related to a boundary integral around the boundary of the computational domain. So let's start here with the generation vector G. And again, we will do this by splitting up the area integration over each element. So you can see that we're first going to have to figure out how to come up with the element generation vector, and then we'll add them all together element by element until we get the global generation vector. So here's the element generation vector, right? So this is the generation vector put together in one element defined by nodes I, J, and K. So within that element then, we'll do a couple things. First of all, we'll say that the volumetric rate of generation isn't going to change inside the element, so it can be pulled out of these area integrals. And second of all, we'll recognize again that within an element, only Wi, Wj, and Wk are non-zero, so this becomes a large vector, but there's only three non-zero elements, and those are in rows I, J, and K. As shown here. So we know how to do these area integrals of interpolating functions. Here's the rule. If we apply this rule to these three integrals, we see that this is this specific case where a is 1 and then b and c are 0. So if we plug that into this equation, we find that this area integral is just the area of the element divided by 3, and that would be true for all three of those area integrals. And so with that substitution, this is what the generation vector looks like inside of the element. It's the generation, the volumetric generation in the element multiplied by the area of the element divided by 3. And then there's a 1 in rows I, J, and K. And again, if you look at this, you'll realize that the total sum of all of the elements, of all of the entries in the element generation vector is the generation within that element, right? Because we have 3, and then we're dividing by 3 here, so we get the volumetric generation times the area. So it's sort of like the capacitance matrix in the sense that you have the total generation, and you're dividing into 3, and you're taking a third of that and plopping it into node I, and then a third of it into node J, and a third of it into node K. Alright, so now we can move on to the boundary integral. So that's this term way over here to the right, and it's related to the integration of the heat flux normal to the boundary. So if you remember, we defined the heat flux normal to the boundary as being normal inwards, as shown here, and that heat flux can be related to either a specified heat flux that you have on the boundary or to convection to the boundary, right? So here we've added up the Q sub S and then H times T infinity minus T, and that's the total normal heat flux. So we'll plug that into our boundary integral, and that turns it into this equation here, which we can break into its 3 separate integrals. So we have the integral of the specified heat flux, the integral of H times T infinity, and then we have the integral of H times T. So let's remember what this T is, temperature, right? Temperature, our formula for it is W transpose times the vector T, where W is all these interpolating functions, and the vector T is all the nodal temperatures. So if I make that substitution into this last integration, I get this. So I have a specified heat flux vector Q sub S, I have H times T infinity, which is also a vector, and then this last thing we're going to turn into a convection matrix H multiplied by the vector T. So we're going to have to do this boundary integral boundary segment by boundary segment. So that's another sort of characteristic that your mesh will have, right? So this is just a reminder of what a very crude mesh might look like. This mesh has 10 nodes, and they're connected to one another in order to form triangular elements. So we've already talked about how this mesh has 11 elements, right? So when we're constructing these matrices that have to do with area integrals, like the capacitance matrix or the conductance matrix or the generation vector, we'll do that in 11 steps, because we'll be doing that element by element, right? So it'll take 11 steps even though there's only 10 nodes. When we start to think about doing these boundary integrals, we're going to have to keep track of how many boundary segments this mesh has. So this mesh has 7 boundary segments that are shown here, and these are the segments that explicitly lie on the edge of the computational domain. Each boundary segment is defined by 2 nodes, I and j, right? So if you think about what our interpolating functions must look like on this boundary segment, the only 2 interpolating functions that'll be non-zero will be wi and wj, right? Because we're moving along that line that corresponds to the base of this element that would otherwise be ijk. And along this line, wk is 0, but wi and wj must be going from 1 to 0 and then from 0 to 1. So let's start with the specified heat flux vector, right? So again, we're going to take this global specified heat flux vector, which is a line integral around the entire boundary, but we're going to deal with it one boundary segment at a time. And again, we're doing that because along any one boundary segment, the behavior of the interpolating functions is pretty easy to understand, right? So we're splitting this up into n sub b little steps, right? We're going to sum up the boundary specified heat flux vectors, and that's what's shown here. Along that boundary, again, we're going to do a couple things. We're going to, first of all, constrain the heat flux to be constant, not necessarily everywhere, but along any one boundary segment, that heat flux is going to be constant, so we can pull that out of this boundary integral. And the second thing is we're going to recognize that on that boundary segment defined by nodes I and j, only w sub I and wj won't be 0. So this w, this vector of interpolating functions, is only going to have 2 non-zero elements, and that will be in row I and in row j. So first of all, then, to finish this, we'll have to figure out what those look like. And it's, I think, pretty obvious that if you're moving along this boundary segment, so if you define some parameter or coordinate s that moves from I to j, you're going to be, first of all, moving from s equals 0 when you're at node I, and you'll be at s equals sij when you're at node j, and sij is just the length of this boundary segment, right? And if you move from node I to j, the weighting function I must be going from 1 when s is equal to 0, and it decreases down to 0 when s is equal to sij, right? So that's just sort of, again, remembering that these are linear elements, right? So we have to integrate w sub I ds as you move from I to j, and that's just the area under this curve. The area under this curve is pretty obviously just sij divided by 2, right? It's the base times the height divided by 2. The base is sij, the height is 1, so it's sij divided by 2. If you wanted to integrate if you wanted to integrate wj along the same path, this is what wj looks like. It goes from 0 at node I up to 1 at node j, so it's the same thing but just flipped vertically. It's also going to be sij divided by 2. So if I want to make those substitutions back into this specified heat flux vector for one boundary segment, so q sub s superscript b, this is what I get, right? I get q sub s along the boundary times sij divided by 2, and then there's a 1 in row I and a 1 in row j. And I guess if you look at this, you realize that once again what you're doing is you're calculating the total amount of heat flux or heat transfer along that boundary, right? So that would be q sub s times sij, and then you're just taking half of it and applying it to node I, and you're taking the other half and applying it to node j. And the other thing to recognize is that, again, you're summing this boundary segment integral, or the boundary segment vector, up, right? So I'll be constructing this global specified heat flux vector in 7 steps in this case, right? 1 for each boundary segment, and I'll just be adding these together. And so I'm not filling in rows, right? So I have to make sure I don't overwrite existing entries as I'm building the specified heat flux vector. All right, so we have 2 more to do. The other one that's pretty easy is the h times t infinity vector. So this is the integral of w times h times t infinity along every boundary segment. So again, we're doing this boundary segment by boundary segment. We're going to make h and t infinity be constant along a boundary segment, so they can be pulled out again. So we're doing exactly the same integrals here in rows I and row j, and these will of course each be a half, and this is the answer then. It's h along the boundary segment times t infinity along that boundary segment, and then the length of the boundary segment divided by 2, and then there's a 1 in row I and a 1 in row j. Okay, and to get the global h t infinity vector, you'll just add up all of these boundary segment h t infinity vectors. So that leaves us with one last thing, which is the convection matrix. So this is the last term that we have to deal with. This is h times t. So this is the integral of w times h times w transpose times t, right? W transpose times t is our approximate temperature. So we got to remember here that this t vector is the nodal temperature, is a vector with all the nodal temperatures, and the nodal temperatures can themselves only be a function of time. So I'm integrating along a boundary. I can pull those nodal temperatures out of that integral because they're not a function of position. So that lets me write this again as this. So this is t, the t vector, and then this thing in brackets must be the convection matrix, right? So w times w transpose is going to be a matrix, right? W is n by 1, w transpose is 1 by n, so that's going to be an n by n matrix that we call the convection matrix. So again, we will put this together boundary segment by boundary segment, right? So I'm doing this for a given boundary segment, which means that the heat transfer coefficient is going to be constant along that boundary segment, and it also means that w is only going to have those 2 non-zero elements in rows I and j. Right, so that's what I have here, and if I do that matrix multiplication, what you'll find then is that this is an n by n matrix, yes, and that can be a very large matrix, but there's only going to ever be 4 non-zero elements in that matrix, and those will be in row I column j, and then row j column I and row j column j. So these are the 4 integrals that we have to do in order to finally construct our convection matrix. And these aren't very hard integrals. Just to remind you, this is what wi looks like along the boundary segment, and this is what wj looks like along the boundary segment. So wi is just 1 minus s over sij, right? So that's going to start then at 1 and decrease to 0 when s gets to sij. Wj is just s over sij, starting at 0 and going to 1, right? So if I want to do the integration of wi squared, that's just 1 minus s over sij squared. And if you expand that and then integrate each of these terms separately, you find that this is just sij, so the length of that boundary segment divided by 3. And I can do the same thing for wi times wj. In this case, it would be 1 minus s over sij multiplied by s over sij. So you expand that, and you integrate it, and you find that that's sij divided by 6. So if I make these 2 substitutions into my convection matrix, this is what I get, right? The convection matrix is going to be the convection coefficient along the boundary times the length of the boundary divided by 6, and then I'll have 2's on the diagonal, so I and jj, and I'll have 1's on the off diagonal. So this would be ij and ji, and again we're just adding all of these up to get our global convection matrix. So at this point we're pretty much done, right? We have our original finite element equations that we got that corresponded to area integrals, and then also to a boundary integral. And we said that these are consistent with a set of matrix equations shown here. So we have capacitance matrix, we have our conduction matrix. We know how to build those. We have our generation vector, and we talked about how to build that today. And then we have the specified heat flux vector, this HT infinity vector, and finally our convection matrix H. Right. So that's exactly the form of the equations that we got for finite differences, and we get the same ones for finite elements. The construction of these matrices and vectors is different. I think a little bit maybe more difficult to understand, at least at first, but certainly understandable now, and we know how to put these all together. We can put them in exactly the same form that we were dealing with for finite difference problems, right? So this is C times dt d theta plus our stiffness matrix S times T, where S is the sum of whatever conductance matrix and convection matrix we have. And then we have our right-hand side vector, our loading vector, which is related to the forcing functions in our problem, which are generation, specified heat flux, or some kind of external temperature. So as we move forward, then the next thing we got to talk about is how you take a mesh, right? So how you take the information that would specify a mesh, which is going to be put into a very specific format, right? It's going to have to do with what points specify the nodes, and then how they're connected to specify elements, and then how they're connected to make boundary segments. And that information you would get from any kind of a mesh generator. But how you take that information and then use it in a very prescribed way to get these different matrices and vectors that we have listed here. But after that, then any of the techniques for moving forward in time, or for having time-dependent forcing functions, or any of those kind of things that we talked about in the context of a finite difference set of equations, you can use exactly again here for these finite element set of equations.